My name is Darshal, and today's talk is about Tensor implementations in Malt. Malt is a library for machine learning, and it was written so that Dan and Anurag could explain how to do machine learning without knowing much high-level math. So the focus of Malt is on simplicity, and it's got a minimal interface. I'll go through the two most important features in Malt today. I'll explain how the interface works, and after we've understood how the interface works, I'll go through the code for how we implement that interface in 3 ways currently in Malt. And in the end, I'll talk a little bit about what I did this semester to parallelize Malt so that it runs faster. Right. So first set of features that first set of interface functions relate to a feature in Malt, which we'll call, which people might know as automatic differentiation. All right. So we have a few familiar functions with different names. So most of this is going to be racket code. Right, so we have a function called square root 0. It's similar to racket square root function, but it does something special. We will see what the special behavior is. There's plus 0, 0, and there's times 0, 0. Right, so what we are doing is we are multiplying 10 with itself, and then we are adding the result with the square of 20, which is done by multiplying 20 with itself. And then finally we are taking the square root of that result. And right, you know what, I'll use some better numbers so that my square root comes out to be a whole number. So let's use 3 square and 4 square. And as you know, the Pythagorean triplet 3, 4, and 5. So the result that you'll see in Malt will be 5. But in actuality, actually what Malt does is it returns a structure called a dual. And a dual contains 2 parts. The first part of the dual is called the row. And there's another part of the dual which we call the kappa, and it's just a function with 3 arguments, and it does something. Right, and we call this function the kappa. I'll go into more detail what this kappa function is, or why this function is called kappa. But before we go any further, this special function that we use here, they're called primitives. So what primitives do is when you give them arguments, they do the same computation as you would expect them to do, but they also return this weird kappa function, and this kappa function stores all the computations that were done in order to produce the result phi. So this kappa somehow remembers that phi was produced by multiplying 3 and 3 and then adding it with 4 square and then taking a square root of that. And the reason kappa remembers that is because we need that to compute the gradient of this function. Let's call this function the distance function. So yeah, so it's better to abstract our functions always. So we'll call this the distance function. Right. So how do we compute the derivative of the distance function? We have a function which Malt provides, and it's called nabla. It's just the Unicode symbol nabla, and it takes 2 arguments. It takes it takes a function as input. Oh, but distance is not a function yet. I actually need to turn it into a lambda so that I know what the inputs are. So, right. So the way Nabla works is that it only takes a function with a single argument, and that argument is usually a list. So so the way I'm going to pass my arguments are in the list x. So I'll do a list ref x0 to get the first argument, and then I'll copy the same thing here. And we'll do the same thing for the second times. Right, and this time we'll fetch the second one by accessing index 1. Right, so how do we compute the derivative? We pass a function and we pass the arguments. I'm going to pass in 3 and 4 as a list to Nabla. And what this does is, since we know, right, so I'm going to, it will give us a list, and Nabla computes the partial derivative of distance with respect to its first argument and then its second argument, or as many arguments as you pass in this list. So in this case, it just gives you 2 results. So the first result is the partial derivative of the distance function. I'm going to use math notation now so that things are easier to understand. And so x sub 0 is basically notation for list ref x0, and sub 1 is list ref 1. Right, and then the second partial derivative is with respect to the second input, x sub 1, and the input function is still the same. Right, and by chain rule, so chain rule, just a refresher, chain rule basically says that if you have a composition of 2 functions, f of g of x, then the partial derivative of that with respect to the input x would be the same as the partial derivative of f with respect to y, f of y with respect to y times the partial derivative with respect to x of g of x, where y is just g of x. So according to the chain rule, what we do is compute the derivative, which is so the derivative with respect to y, which is g of x, right, so our input is this term, x squared plus x1 squared, x0 squared plus x1 squared, and then we multiply that with the function, take the derivative of that function, and then multiply that with the derivative of this with respect to our original input x0. Similarly, we'll do the same expansion for, I can just copy this right here. Except this time I'm going to do derivative with respect to x1. Right, and I think we know that the derivative of square root of some input is the same as half times the reciprocal of the square root. And the result of this would be just 2 times x0 because x1 is considered as a constant. Right, so similarly we have the same term here. Right, and then we just swap in x0 and x1. x0 is 3 and sorry, yeah, x0 is 3 and x1 is 4. So that would come up to 0.6 and 0.8 if you do the calculations. Right, so that's how the nabla function works. And now we had a function distance which takes scalar functions, and yeah, and it's made out of functions that are primitives. So let's try to get into what primitives are, or how can you create primitives in Malt. So the 3 primitives that we use in our distance function are square root 0, plus 0, 0, and times 0, 0. So the way we create that is using a function in Malt called prim2 and prim1. So prim2 creates a binary primitive by passing it some row function, which is what happens when you just call the function normally. So we define plus 0, 0 using prim2. It takes a row function plus, and it takes a nabla function which determines what this function on its own, like how do you compute the derivative of just this function on its own. So A and B are the inputs, and Z is supposed to be the chain rule accumulator. So in chain, so what we are doing here is reverse mode automatic differentiation. So we are computing the gradients from left to right. So Z in this case will store the gradient of this term here, where F is the term that we are trying to create the primitive for. So yeah, so since plus is a binary function, it should return 2 values. So we use brackets values feature to return 2 values, and so the derivative of plus with respect to its first argument is just 1.0 times z. So right, because a plus b derivative with respect to a will just be 1 because b is a constant, and then you have to multiply that by z because of how chain rule works and how you need to build up the multiplicative accumulator. Similarly, for the derivative of b, we just multiply z with 1, and we could have just left z as it is, but just to make it explicit, written the times 1. So this is the row function, and this is the nabla function. So we'll use these terms again later on. Right, so similarly, creating the times primitive is also not that different. We call prim2. The row function will be the racket times function, and the nabla function will be this, and right, so a times b, the derivative of that with respect to a would just be b because there is a constant. So this will be b times z, and for the other side it will be a times z. Right, and for unary functions like square root, we have another function called prim1. Right, so prim1 takes, maybe I should write this on a new page. Right, so prim1, the row function of prim1 is just the racket square root function. And yeah, the nabla function is, right. So since this is a unity function, the nabla doesn't need to return two values. So you just return the derivative of square root of a, so you don't even need the b. Right, so this is actually z times 1 over square root of a, which is basically z over square root of a times 2. Right, so this is how you construct primitive, binary and unary primitive functions. I mentioned primitive as a interface function, but it actually breaks the interface because sometimes to implement a primitive function, you need to know how the implementation is implemented. So we have provided a few primitive functions in Malt, but if we just hid the primitive function from you, then the user doesn't have any flexibility to create their own primitive functions. And sometimes just directly defining a primitive rather than defining it as a composition of other primitives is leads to faster execution. So we leave that power with the users, with the small disadvantage that you have to break the abstraction.
I'm sorry, there are a few messages in the online chat. So could you please look at the online chat, because
right.
I think a few people are having
I
trouble with
forgot
Zoom.
to join the Zoom call once again.
Yeah, I think like 2 people are having trouble with Zoom. You know.
Can you just ask the
let's
question?
see.
You can answer that. Or do you have a question from the chat? From the chat. So what is the question?
Maybe you can just read the questions instead of having Darshal disconnect?
I think the question is that they are wondering about the Zoom link in the announcement email, and they are trying to connect Zoom of some kind.
Yeah, my bad.
I think you
Yeah,
probably
do this.
had a link in the you probably had a link in the announcement email, and they are
Yes, I'm trying to connect to that. Yeah, sorry about that.
Or I guess I can just tell them that like the talk will be recorded and they don't need to worry about Zoom.
Oh
at this
yeah,
moment.
I'll mention that as well.
Okay.
Yeah. But yeah, that's great. That's
Okay,
great.
so let's continue.
Yeah. Let's see. Okay, so I'm in the Zoom call and yeah, they can join the Zoom link now. And I'm sharing my screen. Yeah. All right. Okay, so right, so that was primitives and how primitives can be used to compute the gradient. Next thing I'll talk about is rank polymorphism. Right, so what is rank? So before I go into rank, I'll talk about what scalars are. So here are a few scalars which you can write in bracket. And scalars are basically just real numbers. So any real number will do. And right, so using these scalars you can construct tensors using the tensor function. you can pass any non-zero number of scalars to it to give you to form a tensor. You can also pass tensors as an argument to tensor to create a higher rank tensor. So let's call this tensor T. Right, and we have a function called rank that shows us how deeply nested a tensor is. So rank of T is 2. Similarly, rank of a singly nested tensor or no nesting, tensor with no nesting is 1. Then we have an interesting property that since, right, there's a property that says that the elements of a tensor, elements are members of a tensor, have the same shape. So by shape I mean they should look the same. So what a tensor, right, so for a rank 1 tensor like this tensor 1, 2, 3, its element should be a tensor of rank 1 less than that. So since this is a rank 1 tensor, the tensor containing it should be a rank 2 tensor. So similarly, since this is a rank 1 tensor, a scalar should be a rank 0 tensor. So that's why rank of any scalar will be 0. Right, and we have a shape function that gives you the shape, the same shape as this shape of any tensor. So shape basically says at every dimension or at every nesting level how many elements do you have. So so for our tensor T, at the topmost level we have 2 elements, these 2 tensors, so we'll write down 2. Then at the inner level we have 3 elements, 1, 2, 3. Similarly, the second element of the outermost tensor also has 3 elements because of the same shape rule. So the inner inner member of the list, shape list is 3. So T has shape 2, 3. Right. So now we'll get into rank polymorphism. So for rank polymorphism, we'll invoke a few more special functions, and we'll define another function similar to distance.
Darshal?
Yep.
Apparently the link you use is different from the one you sent on the email. Can you please post the current Zoom meeting link on Discord?
Okay, sure.
Thank you.
Okay, right. So, yeah. So I'll call this distance hat, and it will use a somewhat different set of functions in its definition. I'll call this D, preface these with D. So they are basically calling the same base functions, but they have a special property. And what property do they have? Let's see. So first let us try to figure out what these functions do on their own. So the square root is similar to square root, except that it can accept tensors of any rank. So that's what I mean by rank polymorphism, meaning a function that accepts a a tensor of a certain rank can also be made to accept tensors of higher ranks. So square root accepts scalars, but in our case, square root, the d square root function can also accept rank 2 tensors or higher rank tensors. So as an example, I'm going to use this tensor. So I'm going to get really tired of writing tensor everywhere. So I'm using square brackets to mean that these are just calls to the tensor function. Right. So there's this concept of descending. So right. So our square root function will try to descend into the inner tensors, meaning d square root will try to get applied to every element in the tensor, which is marked as blue. So we push the blue brackets outside, and then apply d square root to every tensor element. Right, and now that we have another invocation of d square root on another tensor, so we'll try to descend again into every element of the blue marked tensor. Right, so we push the blue parentheses, blue brackets outside and call d square root on every element. You get the idea. Right, and now that d square root is being applied to a scalar, d square root is made as square root 0 as the base function. So the 0 in square root 0 indicates what is the base rank that the square root function can be applied to. So now we'll finally swap all the d square root with square root zeros. 1, then yeah. So we swap all the d square root with square root zeros, and finally we get a tensor with elements 1, 2, 3, 4, 5, 6. So in essence, what d square root did was map the square root function over each scalar. But we might have some primitives that work on higher rank tensors, like a primitive that adds the elements of a rank 1 tensor. So in that case, you would stop at this step. If instead of d square root we had d sum, and d sum would just add up all the elements over here. So for now we'll keep it easy and work on just scalar base functions that work on scalars that have been extended. Yeah, this term, so we also call it extended function. So d square root is the extended version of square root 0. Similarly, let's have a look at a binary extended function like d plus and d plus. So it's pretty obvious that if I have d plus 1, 2, 3 and 4, 5, 6, like 2 tensor arguments, then the answer is obvious. You just add 1 and 4, 2 and 5, 3 and 6. But let's try to make things interesting by having 2 different ranks of input tensors. So let's see what the descending algorithm looks like for this. So the descending algorithm first checks for the number of elements in, it checks if the rank of the tensor is the base rank. So neither of the input tensors are scalars, so we won't call the base function. Next we check if the length of the elements in this tensor are the same. So the left hand side tensor has 3 elements, the right hand side tensor has only 2 elements. So we won't descend into both, which is what would happen if you had 2 rank 1 tensors. You would just descend into both. But in this case, we'll just descend into the right side. So mark this with blue. So what happens when you descend only with one argument is that you do the same thing, you move out the blue brackets outside, but you call d plus with the non-descending function on both the elements of the tensors, of the descending tensor. So this is so it's like applying a curried version of d plus with 1, 2, 3 on both the elements of the high rank tensor. So d plus 1, 2, 3 gets applied to the second element, which is 7, 8, 9. Right, and now that we have, so both the tensors now, tensor arguments, now have the same number of elements, which is 3 in both the invocations to d plus. We will now do descend both, meaning that d plus, not curry d plus, but d plus itself will be applied to 2 arguments one by one of both of its tensor arguments, 2 elements each of both of its tensor arguments. That's a handful, mouthful. Let's see. Right, so since we are descending into both, the 2 blue brackets will count as 1. And d plus gets applied with 1 and 4. D plus then gets applied with 2 and 5. D plus gets applied with 3 and 6. Similarly for the second invocation, D plus is applied to 1 and 7, 2 and 8, and 3 and 9. Right. Okay, so now the result is obvious. You just swap d plus with plus 0, 0 because you have scalars now, and it's 5, 7, 9, 8, 10, 12. So this is how rank polymorphism works. So now that we've worked with simple function.
I have a question.
Oh yes, sorry.
Can you just say again why, in the very first step here, why did we choose to descend on the second argument?
Oh, why did we choose to descend on the second argument? That's right. We try to shrink the rank of the higher rank tensor. So we chose the second one because it has a higher rank. Yeah. So that like structural recursion has to end. So we chose rank as the measure on which we decide when the recursion ends.
Okay, so it's just the rank, it's not like the length and
the length is only used to decide when to do a descend left, right, or if you want to descend both.
So if they have equal rank, you do both?
Yeah, you do both.
Okay, you do a higher rank.
So this is not the only way to descend. This is the way we chose in this library. Yeah.
Sure.
So if you flip the arguments, you get the same result.
If I flip the arguments, I do get the same result.
Okay.
Yeah, I'll leave it at that. Yeah.
What would happen if we never got to a point where it had equal or same number of elements?
Right, then you get an error.
Okay.
Yeah.
What?
Yeah. So some shapes are incompatible. Yeah.
But if you have not 4, 5, 6, 7, 8, 9, but add to that 10, 11, 12,
That would work.
that will work giving 5, 7, 9,
8, 10, 12.
and
And
then
then-
whatever, right?
Yeah, add 1, 2, 3 to
Okay.
yeah,
Okay.
10, 11, 12. Yeah. So yeah, that's how you would extrapolate how it works. Yeah. So let's try to see what happens with the distance function now. So now we have the distance hat function. Let's look at its definition again. So distance hat takes a list x and just does the same thing but with the d functions. Takes the square root of the sum of the squared of the inputs. Right. So let's try to give it an interesting input, which is 3, 5, and 4, 4, 12, 12. So I wanted to choose an input that is easy to process, so I to repeat these two numbers, but I'm going to add a mark next to these two, just so we know that they are different. Right. We'll see why we need those marks. Right. So now we try to unfold the definition, which is here. Right. So what happens here is we are trying to multiply the tensor 3, 5 with itself, and here we are trying to multiply this tensor, which we have here, with itself. Right, so there are, yeah, I just swapped in the arguments. Yeah, so let's go from inwards. So we leave square root and d plus as it is. We'll try to focus on d star. Right, so we know that d star first checks if the two lengths are the same. 3 and 5, 3, 5, all of course have the same length, and they have the same rank. So we'll yeah, they also need to have the same rank. Yeah, if I were to tell you this, if the lengths are the same, then we also check if they have the same rank. It makes sense for the operation that we use here. Right, so this basically turns into a tensor where you multiply 3 with 3, then you multiply 5 with 5. Make sense? So I'm not going to evaluate the primitive function because there's a reason for that. But we'll consider the result of the primitive function to be a scalar and think of them as scalar elements of the tensor. Right. Yeah. So, right, so we do the same thing for the second argument as well. Since all the shapes are the same, we'll do descend both until we do pointwise multiplication of all the elements in here. So, since the input is a 2 by 2 shape 2, 2 tensor, the output will also be a shape 2, 2 tensor, where we'll multiply 4 with this 4, this 4 with this 4, this 12 with this 12, and this 12 prime with this 12 prime. So, right, so let me write it down. 4, 4, then we multiply 4 prime with 4 prime, then we multiply 12 with 12, and multiply 12 prime with 12 prime. Right. Okay. Right. So that's D star evaluated until the point where we want it to get evaluated. Then let's do D plus, and we've already done D plus with a rank 1 tensor and a rank 2 tensor before. So what we did in the end was add every element in the first argument of the smaller rank tensor with every element of the second argument twice. So 1, 2, 3, 1, 2, 3 gets added with 4, 5, 6, then 1, 2, 3 gets added with 7, 8, 9 again. So similarly here, what we'll do here is 3 square, 5 square gets added with 4 square, 4 prime square. Then 3 square, 5 square gets added with 12 square and 12 prime square. So right, so we have rank 2 tensor because that's what we get. We get a rank 2 tensor. Right, and we add, I'm just going to say, no, I'm going to write it out because there's a reason why I need this. 0, 0, 3, 3, so this is 3 square, gets added with 4 square. Right, that's our first scalar. At the top left position, then we add yep, 5 square with 4 prime square. Similarly, we do that for the second tensor element. So that's the first tensor element. This is the second tensor element. I'm going to drop the zeros and just write the original function names. So, right. Plus 5 square. Oh, actually, yeah, I made a mistake. I didn't follow the algorithm. Yeah, so remember when I said that this rank 1 tensor multiplied by rank 2 tensor is the same as this case? It's actually not. You don't do a right descent first. So let me go through the step again. So you have 2 tensors. Right, so there's 2 elements here, and then there's 2 elements here as well. So since the length of the elements is the same, you won't be descending into 1.
Yeah, earlier you told Carlos that when the second input has higher rank, you're gonna descend into that one. That's what you said to him, and he checked with you. That's not because of the length, because of the rank.
Yes, that's where I was wrong. That's where I was wrong. You'll notice it when I go through the code. But yeah, forget that I said that.
Planned, no?
Yeah, yeah.
That was all planned, wasn't it?
No, it wasn't.
I was a plant.
No, you're not wrong, dear. Yeah. So sorry. If right, if the number of elements are the same, then no matter what the rank, you descend into both. Yeah. No matter what the rank, you descend into both. Yeah. Sorry.
I'm booing not you, I'm booing that rule.
Oh, I see. Right.
Who came up with that rule?
I would say mostly, sort of not.
So
It gets quite tricky in the book.
Because of that rule.
No, there's so many things going on simultaneously. It's really,
Wait, Darshal, what happens if you can't descend? What if you have a scalar and then a tensor of 1 element?
a scalar and a tensor of 1 element, then you would multiply that tensor of 1 element with a scalar, and you have a tensor of 1 element as a result. So the result is a tensor of 1 element with a scalar.
But wouldn't it try to descend into the, because like it would say that the lengths are the same.
Gets this
Uh,
right.
I'm confused why this is something that, why is there a new algorithm for this problem? This is like, APL did this in the 70s. Why,
Yeah, I'm not sure
why do
if
we need
this is
something
the same as the-
different?
Why would we
Yeah.
read any old books when we have new books to write?
But there's just a lot of systems that provide automatic lifting of scalar operations to tensors over the last 50 years of computer science. How does this relate to them, and why isn't it one of the existing ones?
because the simple answer is I haven't read the existing ones. Yeah.
So is this the algorithm that's in the little learner?
Yes.
Yeah.
Okay, so then maybe this is a question for Dan.
No.
It surely isn't your fault that if it's what's in the little learner.
It's because inside there's some strange things happening that Anurag decided was the right way to do it. Okay? When I work with people, I have to assume they know what they're doing. I'm sorry. Okay? But
That's-
I have to make sure that what sits in the book is correct. Not all the ones that came before it are correct. Just what we were trying to communicate. And it is really tricky. But why don't you turn to the page that has all the answers?
Yeah.
Yes, I'm not sure I understand exactly what the algorithm is.
Yeah. You know what? I'll show you the algorithm then. Yeah.
I don't even know what I want it to be, I just don't know.
You want it so that if you're accidentally having in your training data the same number of features and documents, your code doesn't suddenly stop working.
Sure.
So yeah, this is the learner implementation that tries to follow the specification pretty closely. So let me pull out the descending function. So yeah, here's the descend function. Right, it takes a function g. It takes the base rank of g, meaning when do you stop descending for g. Then you take, g is a tensor and t is a tensor. No, g is a function, n is the base rank for the left input t, m is the base rank for the right input u. Right. And g in our example would be d plus. G in our example would be plus 0, 0, the base function. So what you're doing is you're trying to shrink the rank of t and u until you get to the base rank of g, meaning you try to shrink t and u until you reduce them to scalars, then you can apply g to it. So what happens now is you check if the left input t has the same rank as the base rank n, left base rank n. If that happens, you descend u, meaning you descend into the right argument. If u has the required base rank, then you descend into the left argument. Right, so descend t. So if right argument is already at the base rank, you try to go into the left argument. If left is in the base rank, you go into the right argument. Then you check if both of those conditions are false, that means that none of the left and right arguments are of the base rank. Then you check if their length is the same. If their length is the same, then you map the function g over both the left argument and the right argument. So this is like map 2, I guess. Tmap applies the function g, which is a binary function, to every element of t and u. So if t is a rank 2 tensor, then then g gets applied to the rank 1 tensor elements. That's descend 2, descend both is what I call. And and then there's the case when neither of the 3 cases are true, then you look for which rank is the bigger one. That's when the rank comparison comes in. So if the if the left argument's rank is bigger, that's what rank greater does. Then you descend into the bigger argument. So you do descend t. So if u is the bigger rank tensor argument, then you descend into u. So that's the algorithm, and any other case, it's error. Yeah, I'm not sure if this is what APL does as well.
So what if both T and U have the correct rank? Like what if T has rank n and U has rank m?
Right, so if
Why does this do the right thing?
Right, so this does the right thing because if you look at descent U and descent T, you call T map, right? So, right, you call T map on the tensor. So, in that case, if T is of the right rank, then descent U will call T map on the right argument, and T map actually calls descent again, I think. No, it's just vector map. Yeah. So T map just maps this function with G over to T. So meaning, how do I say
Yeah,
this?
but that seems like the wrong thing, doesn't it?
In fact, there are, if you try this same example in both APL and NumPy or Python, you will get different answers. So,
well, but I mean, it just if, well, maybe I'm just confused. But like G has some base like ranks that it operates on.
Yeah.
And if you pass in both arguments have the correct rank,
Right.
it looks like you're doing some kind of vector map. But shouldn't you just be doing like the base G?
Oh, I see. Right. So we're calling the function descend U or descend T, and G is the base function, and could you repeat your question again?
Like, I guess like back in the original descend function, not yeah.
Yeah.
Like I would have thought that if T and U both have the correct ranks,
Yeah.
that you should just like apply G to T and U. You
Right.
don't descend. Like I expected there to be a first con case that says if of rank MT and of rank MU, then just G to U.
Just apply G
Yeah.
to T and U. Right. So let's see what happens in that case. If T is a scalar and U is a rank 1 tensor, then what descend U does is it applies G to right. It applies. Oh, I see. So, okay.
Or am I not allowed to call descend unless?
No, yeah, you can call it. So my original statement that G is a base function was wrong. G is actually D plus. So it's recursively calling itself. So G is defined using ext2, and ext2 calls descend whenever you pass it the right arguments. So G is actually D plus, not plus 0, 0. So if G is D plus, then performing T map by applying the arguments E and U. So E and U are, so T becomes E and U remains the same. So what is E now? E is an element of T.
Mm-hmm.
So yeah, that caused a confusion, right? So G is actually D plus, and what you're doing with T map is you are applying G with the original tensor U, but on all elements of T. So if T is of rank 0, meaning a scalar, and U is a rank 1 tensor, then calling T map, calling descend T, what it does is, or descend U, what it does is it applies G with the scalar T on every element of U. So D plus, scalar, and every element of U. So if U is, you know what, I should write this down. Right. So if you have, right, if you're calling D plus on, so this is this case that we are worried about, right? When one is of base rank and the other is not.
No, I'm worried about they're both of the base rank.
Oh, I see, yes. So if they're both the base rank, right, so if they're both of the base rank, then you're basically calling descend,
Yeah.
descend D plus with 0, 4, 0, 3, where 0 is the base rank.
Yeah, right.
Right. And in that case, you would call descend U. Right, so you'll call descend U with D plus And I guess you just pass the tensors as they are.
Yeah, but then this is going to be a T-map on the scalar.
Yeah, so
This is what
we're
I'm,
not.
this is exactly what I'm afraid of.
But what does T-map do? For
It's vector map.
Yeah, T-map is vector map. Right.
I think the answer has to be I'm only calling descend if
Yes.
they weren't both.
Right, but yeah,
There it
EXT2
is. There's
has
the missing case. Yeah. So in ext2 of ranks, there's this function called of ranks, which tests if both the base ranks are satisfied or not. So of
Okay,
ranks-
so there is the case that I wanted, it's just in the
yes,
function.
it's
call
outside.
this function.
Yeah,
Okay.
descend is
Okay.
a helper function.
Great.
Yeah.
Just a historical note, you're now looking at approximately chapter 2 at one point. That's scary.
Yeah,
So
actually,
little by little it got pushed, and I think what you're mostly looking at now is chapter 11. Okay. It's very tricky to put all these pieces together and make it make sense.
right. So
That's why I'm telling you, it's a very, very complicated process.
So what I wanted to say was that the way the distance function, the extended function works is that in the end you get a tensor, rank 2 tensor, which takes the distance between these two tensors, 3, 5, 3, 5, 4, 12, 4, 4, 12, 12, whatever. And right, so you don't just get, so as I showed you here, you just get numbers. Those aren't actually numbers, those are duals. Because if you, yeah, that's why I've been preserving the base function invocations. Those base functions actually produce duals, right? So the result is actually duals stored inside tensors. And right, so now why do we need these kappa functions inside the dual? That's because we can, of course, take the gradient for high-rank tensors as well. So with extending functions, we can not only do high-rank polymorphism, we can also compute the gradient for those. So, so the reason why I have to remember what computations those were is because the way we compute the gradient is we need to get two right, we need to get two gradients, one for 3, 5 and one for this rank 2 tensor. So the gradient for 3, 5 has to be the gradient with respect to x0 bar 0. So sub 0 is a list ref, so you access the 0th element of the list, and bar 0 is tensor ref, so you access the 0th element of the tensor. So x0 bar 0 means the 0th element of the list and 0th element of the tensor 3. So we need to compute the gradient of the output with respect to 3. Then we need to compute the gradient of the output with respect to x0 bar 1, which is x0 bar 1, 5. Forget this part. We just care about inputs now. So for this one, we need to compute the gradient with respect to x1 bar 1, bar 0, bar 0. So 0 tensor element 0, tensor element of that as well. So x1 bar 0 bar 0, x1 bar 0 bar 1, which is with respect to this. This element is the gradient with respect to this element. This element is the gradient with respect to this element. And right, and the output is basically this. We have 4 outputs. So with the second inputs is easy. It's easy because this input corresponds to this output in the same position. So right, so x1 0 0 corresponds to the 0 0th element of the output, then 0 1, 1 0 and 1 1. So right, so it's pretty convenient for the second argument because the output also has the same shape. But for the first argument, this 3 gets used twice because we have a step where we did extend once here. So this 3 square gets repeated with this, and it gets repeatedly operated with this as well. So this element gets repeated twice. So the output corresponding to this position and this position, they need to be added up together. So yeah, that's how it computes the gradient. And the way you compute, you produce these extended functions is with functions like ext2. So you can get d plus by calling ext2, giving it the primitive function. This should be the primitive function, and then you give it the base ranks. So yeah, you just copy over these numbers here. That's the naming scheme we've used. Right, and that's the interface. So I didn't get to the implementation, and it's already 1 hour. So I don't know. Maybe I don't know if you want. I could do another talk with the implementation, since the interface is pretty generic. I mean, it's already been done. It's nothing new here. I just wanted people to be familiar with how automatic differentiation and rank polymorphism works. So yeah, thank you. Any questions?
Yeah.